afternoon. My name is Emmanuel Godin. I'm the founder and CEO of PragmaDev. PragmaDev is a company that provides software modeling and testing tools. We'll talk a bit more about that later on, but I want to insist on the underlying technologies we use. I think that's the most interesting thing for you. To specify and to ensure conformance of M2M applications. So a few characteristics of M2M applications first. M2M applications, I guess you can agree on this, are autonomous usually. They have to handle themselves. They're usually quite simple, not always, but quite simple. They must be reliable, and that's very often because they are autonomous, so it's related. And they interact a lot. They're talking to another machine, so by definition they interact a lot, but there's a lot of communication. But even though they are simple, if you put thousands or millions of devices together, then you create a complexity in a large-scale system. So then you might be interested not in the device alone, but in the overall system, and try to see how the overall system behaves. In fact, when all the devices are put together, it might not have the expected behavior. So first, about specifying what an M2M application should do. We distinguish two types of specification. First, define the static interface, and then define the dynamic interface. So I'm not talking here about electrical level interfaces. I'm talking about already software interfaces. So it has to be at digital level. It's a layer 2, from layer 2 to top, basically. So the static interface is a description of the information you're sending to the device, or the information the device is sending back to you. And you have to think of that interface at a logical point of view. What type of information do I receive? And do they gather maybe 5 different informations? What are their types? Is it a date? Is it a temperature? And blah blah blah. And even though this interface must be abstract, I mean, it shouldn't be related to a programming language directly, it still must be translated to the real world. Because at some point you will have to implement the system and it has to work for real. The other aspect for specification is dynamic, because we are talking about communicating devices. You exchange a lot of information, and the order of information matters. Okay? You cannot maybe ask for some information if you don't initialize the device, for example, things like that. So you have to ensure a dynamic interface with scenarios. Okay? And maybe actually the architecture matters. Maybe the device can only talk to a supervisor, not to another device, or maybe it can talk to another device or not. So the architecture also matters. You have to describe all this. And finally, it might also be interesting to describe the behavior. Okay, so what I'm talking about here, it's not only about protocols. It can be also the application. You need to know what the application is doing, and maybe if you have a window, you can open or close. The functionality is open or close the window. It might be very basic, or it might be very complex in some telecommunication equipment, for example. So to describe the static interface, I wanted to talk about ASM.1. Anyone here knows about ASM.1? One? Okay. It's a joint ISO and ITOT recommendation, and the idea is to describe high-level data types. Okay, so it has the basic data types, as you know, with integers, strings, and so on and so on. And you can create subtypes. For example, you could say, "Oh, I have a temperature type, but the temperature type goes from -50 to plus 150." So you can restrict the type to make it fit your real type, I would say. But once you have all these data, all these structures, or maybe strings, or octets, or bits, whatever, you have predefined encoding rules. And that's where it's really interesting. If you use the basic encoding rule, you know that structure will be encoded that way on the basic programming level. So the bit string, or the bit stream, I would say, in the end, is defined by the encoding rule you use. So some of them are standardized, like basic encoding rule, packet encoding rule, XML encoding rule, and so on. So for example, packet encoding rule is the one used for GSM, I think. So it's quite compact, where the basic is quite basic. And XML is very large, because it's a textual representation of the data. And this ASM.1 is quite wide use, even though only one person knows in the room. It's used in the telecommunication, so I'll give you a few examples here, SS7, GSM, and TE. Networking, also in the aeronautic. More recently in the automotive industry with the AutoSAR architecture, I will say a word about that later on, and as well in banking. So
well, most people don't see it.
Sorry?
You don't normally see it.
No, you don't.
So that's why people don't notice it.
But if you have to define an interface, it's very nice. Static interface. Now when it comes to the dynamic interface, we rely on models. So the question of the model is, well, what do we want to describe with the model? Well, basically the model is a way to describe what you want to do, not how you want to do it. So try to avoid to dig into the programming of your device, but try to think about, what do I want to do with my system, and describe what it is supposed to do. And that's a good way to communicate with the stakeholders on maybe subcontractors to discuss what you really want. It will of course help the legibility if you have different systems interconnected. In the end, by experience, we know it improves quality a lot. But I don't know if you know that, but do you know that more than 50% of the software developed is not what was expected? I'm not saying it's full of bugs. I'm just saying it is not what was required in the beginning. Lack of communication. I mean, that's very costly. Okay, so let's build a model. But to build a model, you need a modeling language. And here, we want to describe something that has interactions, event-driven systems. Okay, and usually with that type of situation, we use state machines. They are pretty neat for that. So you can use states and events and triggers, events, and go to another states and send back events and things like that. But then it's not enough, because for example, if you want to like a typical example in a telecommunication protocol would be, I'm trying to connect to a remote device, okay? So I'm sending a connection request, and I'm starting a timer in case there's no response. There's no response, the timer goes off, try again, and then try again. But after, let's say 3 times, or maybe 5 times, I will switch to another mode and say, okay, forget it. I've lost the connection, I will do something else, maybe try another one. But to be able to do that, you need a counter. A counter, you increment, and then you compare the counter to 3. And when you go to 3, you do something else. So you need, in the modeling language, an action language, and that's very important. The model needs to be executable with an action language within it. Otherwise, it will be very poor and merely documentation. So that's what basically we call a formal language. I'm careful with that word because sometimes people think it's mathematically formal. It's not really that. What I mean here is that we have an execution semantic, so we know when it's gonna happen, and it's fully described. There's no hole in the model. So for that, we work on SDL, Specification and Description Language. It's actually a quite old language. Who knows about this? The same one. In the first place, SDL was standardized by ITU to describe telecommunication protocols, and the goal was to describe the protocols sufficiently precise. Sorry?
CCIT.
Yeah. Okay, that was the previous name for ITU, a CCITT. It's an ITU. The idea was to describe the protocol sufficiently precisely. It was not an implementation, still a specification of the telecommunication protocol, but sufficiently precise so that two implementations of the same protocol will, of course, be compatible. And that worked out fairly well. You can see the telecommunication today is working out pretty well. So it's graphical. You can have a graphical architecture. You can have a graphical behavior. It has an action language. So you can increment your counter and compare it with the 3, for example. It has an execution semantic. And it supports ASN.1. Good thing. So I can describe my data, the information I'm sending and receiving in ASN.1 and use it within the model in SDL. And there's also real-time extension that combines code, C code or C++ code within the model instead of the action language if you want something more into, closer to the machine, I would say. Which, I mean, is not the point today. The point here today is describe what we want to do, not how. And, of course, pretty much widespread in telecommunication industry because it has been used in standards, but it's also recognized in the avionics industry. And actually, any event-driven system could be described with SDL. Just to show you how it looks like, you have blocks, like many languages have blocks. Then the blocks can contain sub-blocks and so on. And within the blocks, you have a number of state machines. There can be one or several state machines, and the state machines are described graphically like this. So here, for example, you have idle state. In the idle state, I can receive this increment or decrement message. If increment, I'm incrementing my counter, so just to give you an example. And then I compare to some value, and depending on the result, I go to another state. Okay? If you want to reuse, there's also an object orientation view. So you have classes of blocks or classes of processes, so you can reuse and specialize the behavior. Just to give you an idea. Now about testing, because we are describing the application. What about testing and checking conformance of the application? Another nice standard, TTCN 3. It was an ISO standard taken over by ITU and now written by ETSI, but anyway, it's a standard. And it is a testing language, so it's a textual language, okay? But it has, within the language, constructions to make the test cases fairly simple. One of the most difficult thing when you write a test case is that you send, for example, a request, and maybe you receive an answer, okay? But in the answer, you have to check a number of fields and stuff like that, sometimes quite complicated. So if you make the verification within the test case, it gets quite, complex because you have to write all your tests and blah, blah, blah. So what they've done here is that they have created what they call a template. And in the template, you get all the complexity of the verification of the information you receive in one line. Okay, all the complexity has been put in the template. So it's organized for that. Then it's also organized to handle several possible receptions, because you send an information and you have alternatives of the possible answers you can get. It has timers and it can execute in parallel to test several interfaces on the device, for example. Okay. Oh, good news! It supports ASN.1 as well. Same data type, which is good because that's the static interface we define in ASN.1, and we can reuse it for the testing and for the model. Okay. It has also mapping on target languages, which does not have a SDL actually, but it's quite unique. There's a mapping to Java, a mapping to C, and so on. So it can be implemented on a real tester in the end.
And I have a last good news. Don't know if you know that, but Ericsson actually contributed a full tool set for TTCN3 to the Eclipse Foundation recently. It's called Eclipse Titan. So it's basically all the runtime, all the tooling for running TTCN3 test suite.
I know.
Oh.
They announced it last week.
Yeah, it's really new.
I was there.
Cool.
So, what are the main features you get of using these technologies? First, and that's what we do as a tool vendor, but I mean, as soon as you have these underlying technologies, that's what it is possible to do. First, you can verify a model, okay? And to verify the model, you can execute it. So we have a simulator, because the language has its semantic of execution. You can execute it. You can set breakpoints. You know what happens between the entities, and you can inject errors if you want. And it's just a simulation environment. Okay, there's no compilation or anything. Huh? So you're just executing the model and verify it behaves correctly. And that's the key feature. The model can be verified. I was saying in the beginning, we're focusing on what we're doing, not how, okay? But still, if the model is right, it's very tempting to use it to generate code and put it on the target, okay? Even though the model might not be complete, you might want to complete it, add a few functions and so on, and put it on target. So it is possible, okay? Of course, it is possible, because the model is quite complete, to generate code, put it on an operating system, on a target, or their target, and build the interfaces with the different peripherals of your device and run it. And of course, that will simplify things, okay? Or you can keep your model and say, this is my reference model. I'm going to subcontract the design, the implementation of the model, and then I will show you later on how we can verify the implementation conforms to the model. So we have an abstract model, an abstract set of test cases, and actually the test cases, you can simulate them like you can simulate the model. So actually very early in the V cycle, very early, you can execute your model and run it against some test cases. Or you can generate code out of the model, or you can generate code out of the test cases. I'm not saying you should do everything. I'm just saying you can do, just to show where they are in the development cycle. Another thing people like to do is, because the model has its own execution semantic, they like to verify things on it. Okay, and for this there are two techniques. The first one is exhaustive simulation. So you take all the possible inputs of the system and you try them all. So of course that generates millions of test cases. That's not test cases really, but of scenarios. Okay? So you're trying everything out. And on the side of your model, you have a set of rules. So for example, you say the system should never be in that state, or the variable should never reach that value, and things like that. Okay? With what they call observers. So each time it tries an input, it will verify the observers. That works on small systems. On large systems, it doesn't work. Okay? It's too large. The number of combination is too large. Another technique is to do what they call symbolic resolution. And with that technique, you see the model as a big equation, the big mathematical equation you're trying to solve. So you have to define objectives. What is a property, really? And verify if the property can work with the model and try to solve the equation. So the complexity is a bit different, but as far as we have tried, it looks more efficient. Because for that, we work with labs. It's quite complex, so we work with the different labs. We are specialized in that technology. We just export, our model in their format, and you run there too. As I said before, if you have a model and you know the model is right, and you subcontract your model, if you want to verify the implementation is right, conform to the model, you can generate the test cases out of your model. It's what we call model-based testing. Okay. So we provide that technology in our tool without one of the third party. I have listed in the slide before with the SEVA. We can generate the minimum set of test cases that will cover all the transitions in a model automatically. Okay, so first you verify your model is correct. Your model must be correct, okay? It's a reference model. Then you generate all the test cases that will cover all transitions on your implementation. These technologies, they fit basically any process, development process, and it could be waterfall, a V-cycle, agile methodology. It basically works, because as I showed you on the V-cycle, you can start, for example, testing very early. So even, for example, if you have test-driven process development, it will work. You can start running the test cases before developing the model. Or you can write the model and write the test cases on model. I mean, any solution will fit. It will be in adequation with it. But I'm insisting that, I'm just saying that's the kind of benefits you get of these technologies. You don't have to use them all. Some people just do model-based testing, some people just do modeling, some people just do testing. You shouldn't, well, you could, but it's very rare people who do everything. Okay, a few success stories. This is the Etsy webpage and the type of technologies they recommend. So you see they will list the STL, the ASM.1 and TTCN technologies. Okay, and they recommend that for telecommunication protocols. But as I said, any event-driven application, like an M2M application, will fit. And can be described with these technologies. And by the way, we have also as an example given away with the tool, and actually it's even available on the web. I think the Etsy M2M protocol designed with this technology, ASDN on ASM12. I said a few words about AutoSAR. So AutoSAR is a worldwide partnership of car manufacturers so that they have an architecture common to all equipment manufacturers, so they can choose whoever they want to put in the car. And around 2,600 functional conformance test cases are specified in TTCN 3. So as I said before, they're using ASM.1 and TTCN 3 for conformance to the AutoSAR standard. And the execution of these test cases will be done by test agencies. On the avionics side, there's also, let's say, a reference to SDL as one of the modeling technologies for, sorry, it's a quote, developing a model of the system, be able to experiment it with it and analyze it early in the life cycle. So early in the life cycle, yes, you can simulate it, that's what I said. Can really improve the understanding of the system. And as I said, more than 50% of the systems you develop, or the software you develop, are not what was required in the beginning. So understanding of the system requirements, but also can help to find many errors in the requirement specification or design. That's quality part. So you see, they summarize my previous slide in one sentence. Thank you. So from the industrial point of view, I'm giving examples of a few of our customers. I don't have Alcatel here. Alcatel is our biggest customer for telecommunication equipment, but I put two others. One in the avionic domain, Airbus, with the air traffic control. So all air traffic controls within the plane are designed with SDN and ASM.1. They do simulation and they discuss actually with the certification authorities on the model itself. And then they have a certified code generator to generate the code and put it in the plane. So all Airbuses flying today had the same route, I would say. So they all use SDL. Okay. Another example, which is I think a quite nice story. New Logic was a very small company in south of France, and they started in 2001 to develop a new protocol, the Wi-Fi. And they went to the standardization groups, and they were listening to what the discussions were about, and at the same time they were writing down the protocol in SDL, or actually in that case with RT, because they wanted to implement it. So they replaced the action language by C code, but it's the same, let's say, philosophy. And they were just following the standardization meeting, and they actually could verify with simulation the system was correct, and then generate the code and give it, and sell it actually, as an IP to a lot of, let's say, integrators. And they have followed up A, B, G, and so on. I mean, it worked out very well, and now it has been acquired by the Indian company Wipro. Okay, as a conclusion, what I presented to you was the use of standard languages such as ASN.1, SDL, and TTCN 3 for the specification and conformance of M2M applications. That's really important, yeah? Let's make sure we do the right thing. That's what, focus on what we want to do before focusing on how we want to do it. So we have seen how we can work on the static and dynamic interfaces, and also generate or write the conformance test to verify automatically that we conform to the model. I think I'm done. If you have any questions.